that are like this, cross-counter flow heat exchangers. There are also heat exchangers that are with a small disc in ceramic that is rotating and that is used in order to exchange the heat between a cold flow and a hot flow. But I don't have the time to discuss these details, but there are different types of heat exchangers. And that's why they are calling that recuperative or regenerative heat exchangers, because there are heat exchangers that are more called recuperators, and there are heat exchangers that are more called regenerators. But these are really details, okay? Another solution, this is to look at, okay, I have a first possibility, this is to decrease m.f. But I can also look at the problem in another point of view. This is P divided by m.f QCI. And what is P? P, this is in fact PIT minus PIC minus the PFA. Okay? And this is rather small. This is a small quantity. Very often we write that it can be also written minus beta PIC, with beta that is something like 1.02, 0.03, 0.04. So you see that PFA, it is 2-3-4% of PIC. So the most important, let's say, loss you have in the system, this is in PIC, this is to drive the compressor. And PIC, this is equal to what? PIC, this is m dot multiplied by Cp multiplied by TT2 minus TT1. Or if you put TT1 here, this is like this. This is the equation of PIC. M dot Cp TT1 TT2 divided by TT1 minus 1. And this factor is what? This is purely proportional with the pressure ratio and the isentropic efficiency of the compressor. So if you have a fixed pressure ratio with a given compressor, this is a constant. And you see that PIC is just, in fact, proportional with TT1. And how could you increase eta E? This is by increasing the power. And how can you increase the power? By decreasing the power absorbed by the compressor. And how can you absorb less power in the compressor? By cooling down the compressor. So what will be the nice solution? You have a compressor and you decrease the TT1. It's not easy, because TT1 is maybe only 15 Celsius. In the winter, maybe only 5 Celsius. Decreasing TT1 can lead to a danger of icing. It's not so easy to decrease the TT1. You can decrease the TT1 by injecting, for example, water, a bit of water here, under the form of droplets, and these droplets will evaporate in the compressor, and by evaporating, this is reducing the temperature. Or what can you do? You can split up the compressor into two parts. Here you have TT1, you have a PIC1, first part. Here you have a PIC2 for the second part, and you have increased the temperature. Let's call it TT1.5. This one is TT2. And you take here a heat exchanger like this, reducing the temperature TT1.5 prime. That is lower than TT1.5. By taking, for example, what is a very good way to do that, you take H2O from a river or from the sea. And like this, you will decrease this power absorbed by the second compressor. The total power of the two will also decrease, and that will make that this will increase and that will decrease. That will increase. You increase the power and you increase eta E. This is what is called, it's a generic name, intercooling. This is more called pre-cooling. I will not make the difference, but with intercooling, what can you do? You can increase P, and by increasing P, you can increase the efficiency. Okay? You must be very careful when you do such an analysis. Why? Because don't forget that we have always considered that this is constant. Remember the study of the cycles we've done 1 hour ago? The TIT must be high. So you must keep the TIT constant. So TIT is a constant. But if you are reducing this temperature, TT2 will be also reduced. And so, in an intercooled cycle, what will you have? You will have an increase of m dot f. And so, it's not so obvious what's happening with eta E, because eta E, this is a higher P, but this is also a higher m dot f. And you need to see what is the final result. And in fact, when you look at the cycle, you can indeed increase eta E by 4-5%, something like this, 3-4-5%. Okay? Be careful, because in order to be complete, when you are doing something like that, you need to have here a pump. You need to pump water into the system to inject it in the heat exchanger. And this pumping action is also requesting a certain power. And this power should be subtracted from this one. And so this is this result that you should have to take into account. Okay? What you can also certainly do, this is to combine recuperative cycle with this solution. You can certainly combine a recuperative cycle with an intercooled cycle. You can introduce what is called an ECR cycle, intercooled recuperative. Why? This is because it's very interesting to do something like this. So you do something like this. Most probably you will split up the turbine into 2 parts. I will come back on that. And you have a first heat exchanger here with water, and you have a second heat exchanger here with the hot gases. And the air is cooled down here, and it's heated up here. And so you have the recuperation part and the intercooled part. Why is it interesting? This is because, as I said, this is a way to have a very efficient heat exchanger, because thanks to the cooling of the water, the temperature here is lower, so you will have a very efficient heat exchange between the air and the hot gases. And with an ICR cycle, you can certainly reach 50%, 50% more, 50% plus, like this. 50, 51, 52%, most probably. Of course, you need to have space in order to do that, because you have a double heat exchanger here, and you have a heat exchanger with water here, and you need water. What is the typical application of an ECR cycle? This is in ship propulsion. In ship propulsion, you have the sea, enormous reservoir of cold water, and you have enough space, and you don't have problems of mass, because heat exchangers are very heavy, in order to include this recuperative or regenerative part. So you have the WR11, or TF30. These are different cycles existing on the market for ship propulsion that are intercooled, recuperated, that are much better than the basic gas turbine engine. You have also, when you look at the advantages of an ECR cycle, you have the fact that you can increase the power. So if the IC is not active, so you are not cooling down the flow of air between the two stages of the compressor, you have a small p, not a very high eta E, and as soon as you are activating the H2O, P is increasing, and you have a push in order to have the ship cruising at a faster speed, to accelerate the ship. Very interesting solution. It has been adopted by a few navies, mainly by militaries around the world, US Navy, British Navy. There are a lot of users now of the ICR engine. I will not expand myself on that, because it's not an aircraft cycle, but it is a way to improve the basic gas turbine engine. Could we apply that in an aircraft? It would be today very, very, very surprising, because these heat exchangers, like here, like there, it's very heavy. In an aircraft, you don't have water, but you could imagine to have the recuperative part, but it's very heavy, it takes a lot of space, and it makes the problem very complicated. As I said in one of the first videos, I will show you that during the weekend on a podcast, or let's say a PowerPoint with my voice that I will put on different websites. There is a very nice application